All right, and our final problem here is FRQ Part B, number 2. So number 2 was actually on the bottom of the page for number 1, but it did tell you that there is no calculator allowed for this question either. So it gives us a setup. It says the number of mosquitoes in a field after a major rainfall is modeled by the function m, which is defined by this. M of t is equal to negative t cubed plus 12t squared plus 144t, where t is the number of days after the rainfall ended, and we are restricting our domain to 18. I'm just going to add the units on here. So remember, m represents the number of mosquitoes. All right, so letter A. Letter A says, using correct units, interpret the meaning of m prime of 15 is equal to negative 171 in the context of the problem. So using correct units means you want to include the days, the time unit, the mosquitoes, and you want to interpret exactly what that derivative means. So remember, a derivative is a rate of change. So we need to incorporate the whole rate of change idea. We need to talk about the 15, we need to talk about the negative 171, and we need to include the units. So we're going to say something like this. After 15 days, the rate of change, actually, let me change that. We're going to say the number of mosquitoes is decreasing because it's got a negative rate of change. So this is the derivative, and the derivative is negative, so we can say that the number of mosquitoes is decreasing at a rate of 171, and we don't put the negative in here because we already mentioned the decreasing, so that takes care of the negative. And our units would be mosquitoes per day. Is that how you spell that? It's a weird word. That looks right. All right, so we say after 15 days, the number of mosquitoes, because that's m. So if m prime is negative, that means m is decreasing. So we say m is decreasing at a rate of 171 mosquitoes per day. So the 15 is in there, the negative 171 is in there, the units are in there, the context is in there. So that's how you describe what a rate of change would be in a context. That's absolutely something that you could be tested on the AP test. All right, letter B. Letter B says, based on the model, what is the absolute maximum number of mosquitoes over the time interval? So for absolute extrema, we do the candidates test. We set up endpoints, we set up critical points, put them all on a table. So our endpoints are 0 and 18, and then we want to find our critical points. So remember, the definition of critical points is any time where the derivative is either equal to 0 or it's undefined. Now this is a polynomial, so it's never going to be undefined. So we just take our derivative, so m prime. Derivative of this would be a negative 3t squared plus 24t plus 144. We're taking that expression and we are setting that equal to 0. So this I'm going to divide out just because then I can see if it's solvable by factoring. So I'm going to divide both sides by a negative 3. So this is just a t squared. This would be a negative 8t. And then we know it's negative, so divide 3 in there. That would be 48. All right, so that is our new and reduced form of this polynomial. I'm setting it equal to 0 so I can find my critical points. And for my t squared, I start with t times t, if I'm going to factor this down. And these two numbers are supposed to multiply to a negative 48, and they're supposed to add to a negative 8. So that would be negative 12 and positive 4. Okay, so set those equal to 0. I end up with t equals 12 and t equals negative 4. Now when I do the candidates test, I need to stay within the interval that was given to me. So this doesn't count, plus it's negative, and we're talking about days, so that doesn't make much sense anyway. So t equals 12 is our endpoint. So when we are looking for the absolute maximum, it might happen at one of the endpoints, it might happen at one of the critical points. And that's why we call this the candidates test. We have 3 candidates for what the very, very highest point might be. So we set up a table, and that table in the candidates test always goes back to the original function because they're asking what the maximum number of mosquitoes is. So we need to actually know the number of mosquitoes at 0, at 18, at 12. So we're gonna plug that in. Remember, you don't have a calculator, so we're gonna be doing a little bit of arithmetic here. So we have 0, 12, and 18. So we're going to make a table with time and number of mosquitoes. The 0 is going to be easy, right? So the 0, we sub in here, you've got 0 plus 0 plus 0. So there are no mosquitoes when this starts off. Major rainfall, apparently there are 0 mosquitoes to begin with. Then we want to plug in 12 and 18. So we are going to do a little bit of arithmetic, subbing into this expression right here. So we have negative 12 cubed plus 12 times 12 squared, and then plus 144 times 12. So we're having some great times here. Now, here is one thing that I want you to notice, and this is a beautiful thing right here. We've got a negative 12 cubed, and then this is 12 times 12 squared, which is also 12 cubed. So negative 12 cubed, positive 12 cubed, we only have to worry about this, the 144 times 12. So no calculator means that I am freehanding this. Okay, so we have 1728. Okay, so big number here. So now we can do our 18, which is going to be a little bit less fun because we're not going to have that nice canceling thing happening here. Okay, so these values get plugged in. Now let's see if there's anything that I can do at all to simplify this. So we've got, I could like factor out an 18. Let's see what happens there. If I factor out an 18, then this would be negative 18 squared, and this would be plus 12 times 18, and then plus 144. Might help, might not, I don't know, let's find out. So negative 18 squared is one that I should probably have memorized. What is 18? Is that 324? I don't know if you guys have up to 20s memorized, but 18 times 18, I believe, is 324. So you've got 18, so this would be a negative 324 plus, and then 12 times 18, let's see, 12 times 18, I am just plugging into the calculator, which I know is cheating, but it's 216. So you can kind of regroup here. So 12 times 18 would be the same as 6 times 36, which is 216, and then plus 144. So we'll do a little arithmetic here. If we add these two together, we get 360, and then a negative 324. All right, so we get 36, and then we multiply that times 18. All right, so 6 times 8 is 48. 8, 0, 6, 3. Okay, 8, 4, 1, 6. There we go. 648. All right, so that seemed like a bizarre thing for them to do to us on the non-calculator section, but either way, we did our candidates test. Now you know how that works. We are looking for the absolute maximum number of mosquitoes. Now, if you read carefully, they say, what is the absolute maximum number? So the number is the 1728. Sometimes they say, like, when does that maximum occur? And then you would want to give the t equals 12, but they said, what is the number? So we give the 1728. And then it said justify your answer. So this is kind of a weird thing. On the AP test, when you do all of this, you show the candidates test, you make the table, you complete, and come up with your answer. That's actually all the justification you need. Almost every time justification is a sentence. It's an explanation. But here, this is the one and only time I can think of that it's not. And that's because your justification would be like, well, I picked this one because it's bigger than all the other numbers. You don't actually explain it like that. You just say, we should probably put it in a complete sentence, the absolute maximum number of mosquitoes is, that's a great formatted sentence there. Absolute maximum number of mosquitoes is 1728. And then all of this, making sure you've shown all your work, that's your justification. All right, so let's take a look at what part C is. Part C says, for what values of t is the rate of change of the number of mosquitoes increasing? So they want to know, when is the rate of change increasing? Okay, I'm going to bring back our handy little chart. If we want to know when the rate of change is increasing, we could either look at this or this. This is really tough to prove. we're going to show this. We're going to show when the second derivative is positive. So we're going to find the second derivative. We're going to set up a sign chart. So here's our first derivative. We cannot use this. We have to use this version. So we use this version because this isn't the second derivative. I'm sorry, this isn't the first derivative. This is solving an equation after dividing by -3. So we have to actually use this. So taking the derivative of that, derivative of -3t squared would be a -6t plus 24 and then plus 0. So that is my second derivative. If I want to know when it's positive, I need to start by setting it equal to 0, and then I'll set up a sign chart for my second derivative. So solving this is pretty straightforward. I just end up with t equals 4. So that is going to set up my sign chart. So the 4 goes in the middle. Now we have a restricted domain, so you want to make sure that any test values you're using stay within that restricted domain. All right, and I always label my sign charts so you know what you're plugging back into. We want to know the sign of the second derivative. So you don't plug it into the first derivative, you don't plug it into the original. We want to know when that second derivative is positive or negative. So something between 0 and 4, 1, 2, or 3. If I plug in here, say I plug in 1, I get -6 plus 24, so that's positive. Then plug in something here, maybe like 10 is a nice easy number. So this would be -60 plus 24, which would be negative. So this is when the second derivative is positive, this is when the second derivative is negative. Remember, when the second derivative is positive, that means my derivative is increasing, and that is what the question asks me. So I am going to give an interval from 0 to 4. It doesn't matter if you use open or closed intervals. It's my personal opinion that they would be open because you're not increasing at the endpoints, but I've seen both, so it doesn't really matter. So they said just for what values of t, and they don't ask for an explanation, so don't give one. That's a waste of your time. All right, last piece on that back page, letter D. Letter D says, from 0 to 18, the number of bats in the field is modeled by a differentiable function b, where b is a function of the number of mosquitoes in the field. And then based on the models, write an expression for the rate of change of the number of bats in the field at time t equals a. Okay, so it says the number of bats is modeled by the differentiable function b. So I would guess that, you know, they're setting up b of t, something like that. And it says b is a function of the number of mosquitoes in the field. Okay, so we're actually going to rewrite it like that. Because when you write it like this means b is a function of t, but the way they phrased it, they said b is a function of the number of mosquitoes. So that means where there would normally just be a t, it's a function of the number of mosquitoes, so that m of t gets subbed in there. So that's kind of a tricky phrase to turn into an expression, but that's what they mean by that. Based on the models, write an expression for the rate of change of the number of bats at t equals a. So they're asking us to take the derivative of that, and because there's a composition, that's going to require us to use the chain rule. Okay, so they want us to take the derivative at t equals a. So derivative of this, we've got our outside function, so the derivative of the outside function with the inside function plugged in, and then multiplied by the derivative of the inside function. Right, so it looks like that. And they said at t equals a, so we're just gonna plug the t equals a in there. So this would be b prime of m of a, and then multiplied by m prime of a. So it looks like that. So it says write an expression for that rate of change. So I'm not sure exactly how far they're looking for us to go. I would assume you'd be okay to stop here, but they might want you to actually sub m or a into those expressions. So if that's what they're interested in, m of a means plugging a into the original, which would be this, -a cubed plus 12a squared plus 144 times a, and then multiplied by m prime of a, so you take the derivative expression that we had on the previous page right here, and you plug a into that. So that would be -3a squared plus 24a plus 144, and you want to make sure that that's in parentheses. So they might have wanted you to go that far, but I would assume that this would be okay too. All right, so that's our last FRQ.